Welcome to our first podcast of Unit 7, just at the top of page 2. And our focus, a lot of our focus the last couple weeks was on ionic compounds. We named covalents, so we know that covalents are made with two nonmetals. So what we're going to do is look at the bonding and a little bit more details of what goes in the bonding. So Lewis dot, remember, this comes from the valence electron. So having a periodic table out in front of you is probably going to help, because what we need to do is really focus on those electrons. Okay, so to get started, let's just do a quick reminder. We know that for ionics, valence electrons is what group it is. Everything in group 1 has one valence electron, one dot. We use that. Group 2, group 3, yay. Okay, I'm talking about covalence. So remember, covalence, we're talking about nonmetals. So let's not waste our time. Don't know why it's working. There we go. Let's just focus on the dots on the nonmetals. First nonmetal that we can't forget that it's really is a nonmetal, even though we don't know where to put it, is hydrogen. Sorry. It's got one little valence electron. Then let's skip clear over. Boron. Going across the first period. Has 3. Then what do I have? I'm doing this from memory. Carbon would be next with 4. And yes, I am that much of a geek. Nerd. Carbon, what's next? Nitrogen. Nitrogen has 5. Oxygen, 6. Fluorine, 7. We're not going to worry about the noble gases because we're talking about bonding, and they don't want to play when we're talking about bonding. There's an octet rule. Maybe kind of add that. It's just what it sounds like. Octet. Atoms want to have 8 valence electrons around them. So octet, 8 valence electrons. Now hydrogen is a duet, meaning hydrogen can only have 2 electrons around it. Remember that, please? Please remember that. Look at our rules. They're written here. So, what do I have first? First step, count valence electrons. That's where the periodic table comes in. Now, when you start looking, especially final, and we start putting it together, you can't skip this step, whether it's ionic or covalent. It's like, oh yeah, how am I going to know that? Look at that first element, first element, and ask yourself, is it a metal? And then I just wrote right over everything. That's what you ask yourself. Remember that. Is it a metal? Then what? If it's ionic, that's when we use the bracket. That's what you tested on. Those were the brackets. This is going to be our focus now. What if it's covalent? Put the least electronegative needs to go in the middle. How do I know that? Remember, fluorine is the most electronegative, so it's going to be the farthest, and I don't know where that R came from, excuse me, the furthest, you know I don't teach English, from fluorine. The furthest away, and it should be a furthest, fix it, write it how it's supposed to be, away from fluorine. Look at this, highlight, circle. Please don't make me put a sad face on your quiz. Hydrogen is never, ever, ever, ever in the center. Hydrogen also never, ever, 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 ever gets dots. Hydrogen's too small. Don't put more electrons around it than it can. It only can have 2, the duet. So let's kind of look at what happens. Let's look at hydrogen. So over here, hydrogen. It has 1 valence electron. Here's another hydrogen. It has 1 valence electron. So what they do is say, hey, we need valence, let's get together. So they're going to share these electrons. So now hydrogen looks like it has 2 and is stable, has that 2, that duet. This hydrogen is going to get together and say it has 2. They're sharing this right here. This is your covalent bond when you're sharing the electrons. Let's look what fluorine does. Find some space. Look what fluorine does. Fluorine has 7. Fluorine has another 7. We talk about those diatomics. What happens? They want 8, so they're going to share and have 2, 4, 6, 8, 2, 4, 6, 8. So now we say that these guys have formed a bond between here. So this is the covalent bond. Well, we get tired of drawing the lines. What happens sometimes you could show it like this and show that those 2 electrons between them. So anytime you have 2 electrons between an atoms, you are assuming they're being shared electrons. Okay, what we do is we get tired of writing all of those. So what are you going to do? We say a single line, one single line equals 2 shared electrons. So one line equals 2 electrons. Okay, so let's kind of go, this is what we're going to have to do. So we count that. Then what we do is acids. You know what? Let's just not worry about that now. We'll come back when we start doing acids. Okay, what you need to do is get 8 electrons around it. Most important thing, 8 electrons. Okay, there are some exceptions and we'll come back and talk about these, but for right now, 8 electrons. So 2 ways you can get those electrons. They can either be shared between 2 atoms. This line only happens between atoms. Or you can use lone pair. Okay, unshared, these are also called lone paired. They are paired. Electrons always have to be paired, but they're either going to be a shared pair between atoms or you get a lone pair that are just hanging out on the atom itself. So up here, this fluorine, this would be a shared pair. 2, 4, 6, these are going to be your unshared pair or your lone pair. So let's go through these steps. So add up valence. So carbon has 4. It has 4 valence. Each hydrogen has 1 valence, but there's 4 hydrogens. So you add that together, you have 8 electrons. 8 valence electrons are available. Carbon goes in the middle. So you're just going to put a bond around each hydrogen, around the carbons. And you would say, okay, carbon needs to have 8 around it. So each line is 2, so you go 2, 4, 6, 8. Carbon is good. Each hydrogen only wants 2. Well, 2, 2, 2, 2. So you've completed your drawing using only 8 electrons. So this is it. This is the Lewis dot structure for methane, or excuse me, carbon tetrahydride. Okay, water. Let's add them again. Oxygen has 6 valence electrons. Each hydrogen has 1, so total valence electrons available is 8 valence electrons. Okay, now oxygen is pretty electronegative, it's close to fluorine, but hydrogen can never ever go in the middle, so that's why oxygen goes in the middle. We'll put a hydrogen on each side. A lot of times you just space things out. So then we're going, okay, each hydrogen is happy, 2, 2, but oxygen wants to have 8, so 2, 4. Now you fill in the rest with dots. 6, 8. And you really, really need to be thinking pairs. And some of you who aren't the neatest need to get neat because how you draw it really makes a difference. So then you're saying, okay, to double check, 2, 2. Then oxygen needs 2, 4, 6, 8. It's good. And now it's stable. And I did all this with only 8 electrons. Okay, NH3. Nitrogen has 5 plus the 3, 8 electrons. So what happens then? You go, okay, nitrogen in the middle. I'm going to put a hydrogen, put a hydrogen, put a hydrogen. So each hydrogen's good. Good, 2, 2, 2. But nitrogen wants 8. 2, 4, 6. So we have to put the dots to have 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, we can draw them for ions. We said these were covalently bonded. So we add up all the electrons, and this is when we work on our multiplication. So each oxygen has 6 valences. Sulfur is in the same group, so it also has 6 valence. So I have 5 atoms that each have 6 valences, so that's 30 electrons. But remember, that 2 means 2 more electrons have been added. So I have a total of 32 electrons available for me. Okay, the one furthest from fluorine is sulfur, so it goes in the middle. So we're going to put sulfur in the middle. Then you have oxygens. Each oxygen. Each oxygen. Okay, then we check. Is it good? Well, sulfur's good. 2, 4, 6, 8. But each oxygen's just sitting out here with 2. So make it full with dots. 2, 4, 6. There's its 8. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, whoops, those should be dots, 8. And when we grade the test, we do count dots. Okay, so then you double check. This took 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There's all 32 electrons. The one thing, if it's an ion, you just have to say, okay, the only way I could do this is because I had to borrow a couple of electrons from something to be going. So count the valence electrons as you're going through. Okay, well, let's look at what happens. Not everything just has a single bond. And what happens is you can start having more than one bond if you're bigger atoms that can hold more. And with the bond energy, with the bonds, the bond lengths, a single bond is actually going to be bigger, longer than a double, which is longer than a triple. But they are inversely proportional. Single is less energy than a double, so a triple bond is the shortest and most energy. Okay, but how do I know when we do this? Well, count up the electrons. So oxygen, each oxygen has 6 times 2, 12 electrons. So put oxygen in the middle, and I'll show you how we know. I don't know. Let's just double it up like we've said. This is a pencil chapter. Oh my gosh, it is such a pencil chapter. Because look at what I did. 2, 4, 6, 8, 2, 4, 6, 8. Each oxygen is happy, but count up total electrons. You only have 12 electrons. So if I count electrons, 2, 4, 6, 8, 10, 12, 14, that doesn't work. So make yourself a note here. Okay, to reduce number of electrons, use multiple bonds. What that means, I have too many electrons here. This picture, when your picture shows too many electrons, what you do, that's why we have a pencil, you erase 2 sets of dots, and you're going to say, okay, well instead, the way it's going to get that, it's going to get a double bond. So now when I add, again, each line means 2 electrons, so I'm going to go 2, 4, 6, 8. Yay, oxygen's good. 2, 4, 6, 8. This oxygen's good. 2, 4, 6, 8, 10, 12. This one's good. Yay. Okay, look at what happens with nitrogen. 5 plus 5. Each nitrogen has 5. So there's 10 electrons available. Nitrogen. I forgot what Mrs. Mahoney said, so I'm just going to double everything. Okay? And then we've got a built-in, because you go, yay, this has 8, this has 8. Double check. You only have 10 electrons. 2, 4, 6, 8, 10, 12, 14. Ooh, way too many. That's why I use my pencil. Even if I double bond. If I double bond, that'd be 2, 4, 6, 8, 10, 12. Still too many. It's kind of a trial and error sometimes of what you're doing. Again, pencil. So what does that mean? You had to do a triple bond in nitrogen. 2, 4, 6, 8. Nitrogen's happy. 2, 4, 6, 8. This nitrogen's happy. Count total electrons. 2, 4, 6, 8. 10 electrons. Now it's good. Okay. One more, if we look at this, CO2. Add them up. 4 electrons plus 12 coming from the oxygen. So 12 plus 4, 16 electrons. 12 plus 4, 16. Yes, always double check my math when I'm doing these. Carbon goes in the middle. And again, oxygen on each side. I'm just drawing it to check. See if I got lucky. Hoping we got lucky. Okay, then we start adding. 2, 4, 6, 8. Everything has 8, so we've got that half done. Now we add up total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh man, here comes the eraser. So, erase there. Whoa, I didn't mean to erase that much. So what do we have to do? We're going to have to put our oxygen back first. We didn't erase those dots. So if we put a double bond there, each 2 that you want to reduce is 1 double bond. So I had 4 too many electrons. That's how I knew I needed 2 more bonds. You start to figure that out. If not, you can take it one at a time. I'm just trying to speed along the podcast. So if you look at 2, 4, 6, 8, oxygen's good. 2, 4, 6, whoa, not good. See? Count. Double check. So erase those. It doesn't need that anymore. That's why we check. So 2, 4, 6, 8, oxygen's good. 2, 4, 6, 8, now carbon's good. 2, 4, 6, 8, now oxygen's good. Okay, but final check. 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So we did it. Yay! We did it. We made everything look like it has 8 with only using 16 electrons. So let's talk about some of the exceptions to the octet rule. So that means these don't always want to have 8 around it. First one we're going to look and we see sometimes is a beryllium iodide. Now these happen with the larger halogens a lot of times. Beryllium, I know you're probably going, wait, it wants to be ionic. If it's with the halogen that has a really small electronegativity, what happens is when you draw it, and if you look at it, beryllium only has 2 electrons. So beryllium, if you look, only has 2 valence electrons. Okay, let's do the math. The math is still going to make sense. So you have 14 plus the 2, you have 16 electrons available for this. So if I put iodine around it, iodine wants to have its 8, that's not changing. So 2, 4, 6, 8, 2, 4, 6, 8, but count your electrons. 2, 4, 6, 8, 10, 12, 14, 16. That's the only electrons you have. So therefore, that is full. You do not have any electrons, so beryllium does not get a lone pair. Okay, that also happens with the aluminum with a big halogen. More common, let's kind of focus on what you're probably going to see more, and that's going to be a boron compound. Same thing, look at boron's valences. It has 3. Each chlorine has 21, or excuse me, each chlorine has 7. 7 times 3 is 21, so I have 24 electrons available. Boron goes in the middle. You're going to put a chlorine around it. Then each chlorine wants to have 8. So counting 2, 4, 6, even if you forget, you're like, okay, yay, la-di-da-di-da, everything wants 8. When I go back and count, 2, 4, 6, 8, 2, you would go 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. You're going, wait, oh, I'm so confused. What can I do? Okay, remember, boron is an exception. What do? You remember, boron does not want to have 3. There it is stable without the electrons. Okay, there are some times that they get to have a few more. The reality is, let's not worry about those right now because let's just, in pre-AP we're not going to focus so much. Just want to know that sometimes it happens. So if you take AP, you can't say I lied to you. We just maybe didn't tell you the whole story. Resonance we can kind of talk about tomorrow in class. What resonance is if you can draw that double bond in more than one place. So we will see you tomorrow.